You're listening to Gradient Dissent, a show about making machine learning work in the real world, and I'm your host, Lukas Biewald. Today I'm talking with Julian Green, who's a serial entrepreneur who's founded at least 3 companies, House, Jetpack, and Headroom, and has also been the GM of AI moonshots at Google X before founding his current company, Brightband. Brightband's mission is big. It's to provide advanced Earth systems AI to improve weather and climate-related decisions for the benefit of humanity and Earth. And they're taking on a really interesting domain of weather forecasting. This is a cool interview because I get to talk to him about being an entrepreneur in deep tech, as well as a really interesting use case of AI predicting weather. I hope you enjoy it. All right, so welcome to Gradient Dissent. I think one of my favorite kinds of people to have on this podcast is entrepreneurs that are working on a specific, tangible problem that we can all understand. And, you know, we've had people working on industrial farming, we've had people working on designing circuit boards, we've had so many different categories of this genre of person, but we actually haven't had anyone working on climate. And so I wanted to ask you, first of all, what attracted you to the climate space, and why do you feel like this is such a meaningful problem to work on?
Yeah, well, you know, growing up in the UK, maybe it's just because I miss weather in California most days. You know, so it's often sunny and nice, but even in California, you know, we have atmospheric rivers and all sorts of things. You know, I grew up in Oxford and I had a summer job, or a friend had a summer job I helped them with there. And we would go and take readings, thermometer readings and sort of rain gauge readings at a weather station in the UK. And I didn't realize it at the time, but I went back and looked, and actually this place, the Radcliffe Meteorology station has had a continuous rain and temperature, stream of data gathered since 1813. And, little did I know that, when I didn't want to get out of bed in the summer going up. I'm glad I did. We would have broken a long streak. And then, so it's always been interesting to me. I think with the increasingly extreme weather that we see, I think it's really important that we have the tools to be able to, adapt to that extreme weather, and then, if possible, to work out how to mitigate those effects. And I think that's a joint responsibility we all have, and I think AI promises to do amazing things there. So it's exciting. I mean, some of the stats on the increasingly extreme weather are mind-boggling, and we've all seen this summer various hurricanes. But back in the 80s, there was $1 billion disaster every 4 months in the US. Now there's one every few weeks. So
is that right? Every few weeks?
Yeah. And actually, I mean, the ones this summer are not just $1 billion disasters, they're tens of billions of dollars disasters. And these are real lives and real things being destroyed. The World Bank thinks if we could one part of weather, if we could just have more timely and accurate notifications for extreme weather like hurricanes, tropical cyclones, and so on, we could save $162 billion a year in people not dying and assets not being destroyed.
So what's the state of the art today, and where do you think you could take things?
Yeah, so the exciting thing happening with AI in weather has been that there's been this amazing research. I guess backing up slightly, AI has been used for a while in weather, particularly to downscale lower resolution forecasts. And I think of that just like, with computer vision, sort of super resolution, interpolating between the data points you have. And it's been used for some data processing on the front end. But the thing that's happened, which one of my co-founders wrote a seminal paper on in 2022, Ryan Kiesler, is to use AI as a time machine to forecast weather from initial conditions, and to do that in a learned way, rather than the physics approach that numerical weather prediction's been using for 50 years, really since the dawn of computers. And that turns out to be faster, cheaper, and more accurate. So it's sort of crazy that relatively out of the box AI that we've been using has been able to do such an impressive job. And I think it's very exciting where that will take us.
But I guess like tangibly, I'm not even sure what the state of the art of weather forecast is today. I think everyone's probably experienced opening up an app like Dark Sky or Apple Weather and seeing the weather prediction for tomorrow or the next day. Like, has that gotten gradually better? Is that something that your techniques would help with, or are you really focused on extreme weather forecasting?
Yeah. So how good is weather forecasting, right? I think the easy answer is not as good as we'd like it to be. What has happened is each decade, since the sort of use of computers for numerical weather prediction, we've got one more good day of accuracy each decade, basically, right? So if you think about and by good, we sort of mean better than climatology. Right. So one way to do weather is you look in the Father's Almanac and it says today is November 4. And usually on average on November 4, it's this temperature, you get this much rain and sort of a long-term average approach. And you're looking for how many days in the future can you do a better job than climatology or other techniques. Another one is persistence, right? So you just say, well, today is this temperature, this weather, and so we assume tomorrow is going to be like that, right? So you look for where you can do better than those other methods. And so each day since really using computers, we've sort of got it one day better. But that means that now...
That's since 1980 or 1970? Where are you starting?
Well, computers have been used in weather since sort of the 50s, right?
The 50s.
And the approach has been sort of
7 good days of accuracy, or
Yeah.
7 days that you're better off kind of using this method versus just a baseline average.
We're using broad brushstrokes here. Obviously, for different things,
Sure.
you can do better. Like temperature, might be easier than exactly how much rain are we going to get wet, right? But sort of roughly speaking, 7 to 10 days, our forecasts aren't bad. Now, there's a nuance there that relies upon having good observations and good models. And poorer countries, who don't have as many observations and who don't have purpose-built models, their one-day forecast is as good as our 7-day forecast. So that's sort of crazy to think about. So it's very inequitably, distributed good weather forecasting. But if you think about all the things you want to do and all the decisions you have to make that are dependent upon both weather and then climate, having somewhat interesting forecast only out a week is not as good as we would like. We would like to have much more, local specific forecasts. We would like to be able to forecast further out into the future, and particularly with things like extreme weather events where really, things are being destroyed, people are dying. We would like to be able to do a better job.
And so are you focused on these extreme weather events?
We're building our approach, and that's definitely one of the most high value, weather forecasting bits. So yes, we're looking at extreme weather, but we will see what it turns out to be best at. AI has been used quite a lot in nowcasting. So sort of what the weather is going to be like in the immediate future, where the initial conditions are pretty important, and then. The crazy thing has been that as we develop better AI tools, it's been starting to be better than the physics models, which are run, we've spent 50 years getting good at this with the partial differential equations that run on billion-dollar supercomputers, but yet AI is now looking, better from a sort of root mean squared error basis, 5 days, 7 days, 10 days, even some signs that it might be better further out than that. Sort of crossing some lines that we thought had been drawn by maths for chaotic systems, where you may not be able to look further out in the future than some time. Lorentz, looked at this decades ago, and so it's super exciting that AI seems to be able to find signal, beyond some of those limits.
Okay, you're immediately pulling me off script, but that was actually a question I wanted to ask you. I remember my college partial differential equations class, the example was weather. And I think it was even that butterfly example of how, tiny changes in initial conditions can clearly lead to wildly chaotic output. And therefore it's probably impossible to predict the weather, out beyond a certain region. So what's changed, or what was wrong about that theory?
the butterfly effect is real, right? And so, that's sort of a mathematical truth. But, ask yourself how many times when a butterfly flaps its wings, does it produce a hurricane, right? And the answer is not that often. And so really, one of the beautiful things about using AI for weather forecasting is an inherently probabilistic field. And because you can run inference so much faster and cheaper, you can run a lot of scenarios, a lot of ensembles. So right now, physics models are sort of constrained to about 50 production ensembles. And so if you're looking for, a 1 in 100, a 1 in 1,000 storm, and you're only running 50 ensembles, like the chances that you capture, that particular scenario are relatively limited. So that again is a lot of promise there that you can run sort of arbitrarily large numbers of scenarios, really get that whole distribution and then zero in on sort of the anomalies that matter.
Although it's funny, like if you could perfectly know somehow, and I guess this even gets into the theory of probability or something, but if you perfectly knew that there's like a 2% chance of a hurricane, hitting Washington in a week, it's hard to know what you even do with that information, right? Kind of putting medium probabilities on stuff, might lead to, fatigue of emergency forecasting and things like that, right?
Yeah, I mean, so what can one do? So let me give you a couple of thoughts on that. So, Hurricane Otis hit Acapulco in 2023, right? And it did $15 billion worth of damage, and it killed 50 people. And they had 4 hours notice. If they'd had, the World Bank estimates if they'd had more like 1 or 2 days notice, they could have saved most of the lives, because you can move people to safety, and you can board up windows, and you can move cars, and you can move boats, and you would have saved maybe a third of the damage, right? So 5 of the 15 billion. Still going to hit stuff, but you can sort of choose how to protect that stuff. And so, you can do some things. Now, the big challenge, and we see this when hurricanes are circling through the Gulf of Mexico, approaching the shoreline. You're like, where's it going to hit, right? You can't evacuate, all of Texas and Florida or the other states. And so the more accurate you can be, and actually, some of the models for Milton got it within 13 miles, like days out, right? And so then you can say, depending upon how things are set up, we have enough time, because it takes days to get people out of a big city. So we have enough time and enough accuracy to be able to evacuate a manageable number of people in a manageable amount of time.
Okay. So you've been a serial entrepreneur in a whole bunch of different technical domains, including, I remember Jetpack, and House is obviously a well-known company. And then you worked at Google X on various moonshot projects. I'm curious what you're taking from that experience into this domain, and what's already different about this domain where you're operating differently than previous companies.
Yeah, that's interesting. I mean, this is my 6th startup, right? And so the long-term lessons that apply to, all the different things, whether it's books or bulldozers or e-commerce tools or tickets or home design inspiration or travel inspiration or AI video conferencing or, all the different things that I've done, you got to understand where you're making value for users. And so just really being focused on that. With AI in the last, sort of 15 years that I've been doing AI startups and working at Google on AI, AI is amazing at the first 80%, right? And so, ChatGPT, like one of the most, extraordinary technical demos, ever done. And then, how do you turn that into a product, right? And so the last 20%, when you're using a learned approach, the edge cases kill you, right? And so you really got to think about very, very keenly think about what problem are you trying to solve that the AI technology is going to be well suited to solve it. And you pick that right. And then it's got to be one that people care about and that's valuable and that's useful. And you got to work out how you deliver that. And I think, with LLMs, it's extraordinary at generating reasonable looking language very fast. And so for situations where that is a benefit, where the alternative is slow and painful and not very good quality anyway, then that's amazing. Right? And then more objective cases where, we started the generative coding stuff at Google, and, thinking about, it's a very structured bit of language. There's a great data set of peer-reviewed, data, and you've got to be able to run the code, so you have some sort of objective measure of how accurate the language is. That's a great case. Now for weather, it's incredibly data rich. We have 100 petabytes of cumulatively gathered historical weather data, and crazily, we're about to get 100 petabytes every year going forwards. So the advent of these very high definition, radars and satellites, and sort of the scale up of observation means that there's tidal wave of data. And you get another day of ground truth every day. Unfortunately, no faster, but you can find out whether your prediction is good, and you can go back and you can hindcast. So I think it is very well suited, and I talked about how weather is sort of inherently probabilistic, right? And the techniques that you can use, the statistical techniques you can use, which will give you a full probability distribution rather than just a deterministic binary, is it going to rain, isn't it going to rain? Those are very useful. So we're excited about the AI will be able to do a good job in weather. More broadly, I think, the sciences in general, I think are seeing the dawning of an amazing new tool with AI to work out how to improve, both research and applied research.
And so with weather, you talked about physics-based models being the dominant strategy now. I think we've seen in lots of domains things switch from sort of expert-based systems or systems with, a lot of knowledge being put into the construction of them to black box end-to-end trained AIs. Are you also taking that approach? Are you completely disregarding all physics, or are you trying to insert some physical knowledge into your models?
Yeah, this is a really interesting area. I think knowing what we bring to the table is, I think we're trying to bring, AI sort of top talent and trying to apply the latest AI research to this area. And I think that's sort of what we can bring. And so we're going to see how far the sort of the pure data-driven approach can get us. There have been some really interesting applications. Neural GCM is one, where people have taken sort of a hybrid approach using some physics and the statistics. And that is very attractive, right? We sort of know that you could conserve energy, momentum, mass. You can't make up moisture. What is interesting is in the directly, AI approach, it appears to be learning some of those physical laws just from the data. And so, the trade-off, whether the AI approaches are so much computationally cheaper and faster, I think that's a really interesting place to advance. But inevitably, I think there'll be some really interesting hybrid approaches. And prediction of the weather is a somewhat practical applied problem. Understanding the science of the weather, is a different problem and needs a different set of tools. You may be able to inform that with the conclusions of the AI models, but you may also need, physics models to do that.
So you have this big stated mission right now as a shiny new startup. And I've watched weather startups grow over the years. I'm sure you have too. And it's kind of surprising to me, at least as an outsider to the industry, where the business models eventually land. Could you talk about the different ways that a company like yours could make money, and how you're thinking about that, where you think things might end up for you?
Sure, yeah, and it probably helps to sort of understand a little bit, what the weather industry looks like. And historically, it's looked a lot like sort of a vertically integrated, the government does most stuff. And so, you have government satellites, you have, government data assimilation, taking all those observations and getting them into shape for the physics models. And then you have the physics forecasting models, and then they disseminate that. And in the US, there's been a proud history of sort of open weather forecasting data. And then And then there've been commercial companies who have taken those sort of generic government forecasts and have tried to make them useful and put them on the phone and done all sorts of things with them. So that's been sort of the historical picture. And I think what is sort of crazy about how AI will change that is that for the first time, everyone will be able to forecast. You don't have to be a government with $1 billion supercomputer. You don't have to have a satellite. You can take those observations, and then you can use AI to run forecasts on them. So that's going to change the structure. And we think that instead of just one sort of vertically integrated approach, we think there's going to be more sort of layers, as you might see in like in the LLMs. You have, and this very well from your background. You have data providers, you have training tools, you have analysis tools, you have the hardware, the software, various layers of abstraction. So have these different layers, and so that's where we see this going a bit. We're very focused on where AI, and not just AI, but sort of AI and data, because the secret of AI is you really can't do anything if you don't have good data, and even more where we have done AI is where we've had the data. The reason we started with cat pictures is because we had a lot of them, and so I think that our business model will be to focus on sort of the data and the AI and the metrics, and so this is another area where there's been sort of a bunch of there's sort of a temptation to cherry pick, right? It's like, hey, I did great on last Tuesday's storm, so I must be good in general, right? And so what we want to have is sort of a very holistic set of criteria on which to judge AI models and the physics models, and to know where AI is not doing well yet and where we need to improve it. So we're focused on the data, the models, and the metrics.
Okay, but where does that go as a business, right? So I obviously have this. Probably everyone watching this has the experience of like looking at weather applications and forecasting weather. Is that really the best business model here? I mean, I understand that like insurance companies are interested in this. Probably there's applications to a broader set of financial companies. I imagine a lot of businesses are impacted by the weather. Like who really buys the product that you're building here?
So there's a bunch of end users, and it's quite a eclectic group, right? Lots of different end users, lots of different needs. So you've sort of the climate corporation doing farm insurance, crop insurance. You've got energy utilities who need to be able to make sure that their assets will work in whatever weather, that are predicting renewable energy supply and predicting temperature related demand. You got supply chain people who need to know where their trucks and planes can go. You got all sorts of different end users, and they have different use cases for the weather. And I think what has been the case is when you're doing sort of a consultative analytics approach, which has been largely what sort of weather companies have focused on, you sort of get really good at doing one end use case or a couple of end use cases, but it's tough to be everything to everyone in that area. We think, because we're a bit further back in the chain, that there's an opportunity to provide the tools to be able to do forecasts to everyone. And so including, the weather companies who can then serve the end users, and maybe some end users, but providing tools, and that's our approach. And I know that you like that model.
Oh, me? Oh, that's true. That is true. Yeah, I'm not, no judgment. I'm just kind of curious. So, and I guess where I was going with that is, you made this choice to be a public benefit corporation, which is kind of an interesting choice. Maybe you could describe what that is, and then also why that was important to you in your company formation.
Yeah. So a public benefit corporation is actually a C Corp, but with a stated mission. And so the board has a responsibility to not only try and maximize value for its shareholders, but also to maintain the mission. So in our case, democratizing weather forecasting and giving everyone the tools to be able to do that, through our operations and, any acquisitions or changes in control, we need to, as a board, make sure that we're ensuring the success of the mission. There are some people, when I was looking at this and working it out, there's another class of corporation called a B corporation, which many people think about. because it's been quite high profile. And there's a very sort of long list of criteria and that you have to do. So yeah, a public benefit corp is slightly different. You state your mission, you sort of pin your flag up on the flagpole. You report out on that mission each year. And then as a board, you have to take that into account when you're making decisions.
And so how would that affect practically how you make decisions or allocate capital or something like that?
I mean, hopefully if your mission and your commercial success are aligned, then it wouldn't change it at all. And we've set up, what we think is both the right commercial strategy to be relatively open with that technology and to, so interestingly, when you talk to customers, the biggest barrier facing AI weather forecasting is trust. You've got a lot of people who are used to highly successful, physics approach for a long time. And the AI is really interesting, but it's new. They don't know what it is. And these are important decisions that people are making every day about the weather and about climate. So the first thing I think we have to do is to get it in as many people's hands as possible so that they can play with it and learn to trust it. And that approach and open sourcing sort of the basic forecasting technology, I think will help do that. And you've seen in various different AI areas sort of this common task method where you can give people enough data, your model and metrics for them to be able to develop their own models and improve upon that and compare different approaches and really have sort of a sandbox in which to play. So that's what we're looking to do here. Improving weather and climate forecasting is not only going to be achieved by us at Brightband with our relatively small resources. It's going to need the whole community to improve it.
But I guess I'm curious if so public benefit corporation, if what it means is that you need to stay focused on your mission, it seems like almost any startup probably should be doing that or want to do that unless they're making a massive pivot. Is there something about the weather space specifically that made you want to have this structure, or is that something that you would now do with like any new startup that you would potentially start?
Yeah, that's a good question. I think with weather, it's one of the rare examples of successful international collaboration. And one country's weather yesterday is the next country's weather today. So everyone is very incentivized to share weather data, which they have been doing through the WMO and the different Met offices, and that's been a rare, sort of shining example of what you can do with collaboration. And so I think that ethos and the fact that the weather and climate problem that we face as humanity, I think, was the reason we wanted to make it really clear that we're trying to do something for the whole community as well as for ourselves and our company.
I guess one of the things that I found when I was researching weather and forecasting in general is the company you're coming from, DeepMind, has actually done a fair amount of work in this space. They've published some interesting results, kind of along the lines, I think, of what you're saying. Predicting, I think, Hurricane Lee and publishing some papers on this. Are you concerned about competing with a company like DeepMind, which obviously has a lot of resources, especially around machine learning?
As I get older and do more startups, I'm always wary when there's no competitors. It usually means you're picking a problem that isn't
Totally.
super interesting. So I'm not afraid of competition. And as a startup, you bring a bunch of things to the table that other companies don't have. And so singular focus, small teams, really working hard on a single problem. So I think we fill a gap. The big tech companies, weather is not their core business. They do amazing AI research, and we will, and everyone will be great beneficiaries of that. But until it's a sizable business, it probably doesn't make sense for them to focus on it and to get deep enough in the domain to deliver what people really need. So we think we can provide some help there, and then the existing weather companies and the incumbents sort of have the classic innovators dilemma problem, which is they have existing businesses, and this is a completely different way to run your business. And so we think there's a chance that we can make a dent.
Well, I mean, of course, as a fellow entrepreneur, I share your instincts here. But I guess where I want to go with that is, it seems like deep learning and transformer-based architectures feels like maybe a new world where the capital costs are really high. And when you talk about a petabyte of data being created every year, it does seem like your company's
Sorry, 100 petabytes.
100 petabytes every year. The capital costs here seem like they could be enormous, and it could really matter. Access to compute. Do you have a strategy around that, or are you? Yeah, how do you think about that?
Yeah, I mean that's partly why we resourced ourselves relatively well for first round of 10 million. And on the data side, what's interesting is the data is available and is disseminated publicly by the government, and so that helps. And actually through the NOD program, NOAA has disseminated its data to the different public clouds, and that actually was sort of what started this boom in AI, where the forecasting was this analysis database, the Aerified database from ECMWF, became available in a cloud form, where essentially people who were not weather domain experts or weather data domain experts were able to run AI experiments on it. There's sort of an availability of data. We've resourced ourselves to the extent that we think we need to, and this is. People sort of think of the LLM market of hundreds of millions of dollars to train a model, or going into the billions to train a model. It seems as though so far that this is a few orders of magnitude cheaper to do the training, and then the inference is also relatively cheap.
Why do you think that is?
People love to, sort of rationalize this, and I have some rationalizations. I do think, it's pretty hard to predict, and you sort of have to try it.
Totally. Yeah.
But, one rationalization is, with LLMs, you have this tool language, and you're trying to capture everything language can do. You're trying to capture history and culture and sport and, maths and analysis and sort of everything. It's being used as a tool in lots of different ways. To get AI to spot all those different patterns, pulls it in different directions, and so there's a bunch of complexity there. With weather, you have sort of a single geometry. You have sort of essentially a moisture in air system at its most basic, with repeated patterns that repeat every day, and so you're sort of modeling one thing. It's quite complex, it's quite big, but it's a single thing. And so. Perhaps that's why we're finding that AI can do a good job with lower training costs and fewer, based upon the fewer number of parameters that you need in the model to capture those patterns.
Are you more inspired by transformers like language approaches that seem to be all the rage in almost every domain except for numerical time series, or are you kind of leaning on more numerical time series approaches in your investigation here? Like, how do you think about that?
I mean, transformers are great because they're getting so optimized, right? And so if you and some of these architectures start to look a bit like each other. You can sort of imagine a type of graph neural net that is a transformer, and you can sort of they sort of merge into each other depending upon some of the configuration assumptions. So transformers have been used for the weather forecasting, and it's sort of an encoder, a processor decoder type architecture, and the processor people have used vision transformers. Some of the other approaches out there use diffusion models. Imagine trying to guess the next frame in a video is sort of like trying to guess the next frame in a radar picture, but for multiple dimensions and variables. And so the architecture is important, but it's sort of not the only thing. And so we're exploring different approaches, and it will be interesting, as you say. This is a slightly different class of problem. We've seen vision transformers and diffusion models used very successfully for things like CFD, fluid dynamic, simulations, and so on. And really, it's super exciting because there's so much innovation in this area of making these tools more efficient for science problems in general that we and everyone else will benefit from that underlying research.
Do you work on like trying to predict all the weather in the globe at all times, or do you kind of specialize to like, okay, we want to try to predict where this hurricane's gonna go? Like, I mean, I could imagine in some sense those are the same problem, but I would think you would kind of treat those quite differently, if only for the kind of computational resources.
Yeah, so sort of the benchmark task to see if your forecasting tool is any good is sort of the 10-day global weather forecasting, and the resolution of that. Sort of initial models have been at sort of the 1 degree level, which is sort of like 100K, at the equator.
This is 1 degree of like latitude and longitude, is it?
Yeah, of arc. So yeah, 100K at the equator. And then, sort of the state of the art with physics models is more like, 10K at the equator for global weather forecasting.
10K what? 10K?
10 kilometers.
I see. So what's the weather like in a 10 kilometer square?
Of 0.1 degrees, yeah.
I see.
And so that's sort of the benchmark task to, where we have really good, long time frame data, and we can run a hindcast for, a bunch of years and say, okay, on average, are you doing well or not? We're trying to add to that sort of, minimizing error on average approach, the root mean squared error approach. We're trying to add, how right can you be, how opinionated can you be with a sharp forecast on a specific event? So we've sort of taken, a metrics piece, we're taking a bunch of notable weather events, and we're trying to see how well do all the different AI models and all the different physics models do on those, which I think is really interesting, what the weather people actually care about.
Right.
It's nice not to be wrong on average very much, but you also want to be right. So I think that's very interesting. So we're sort of starting with that global benchmark of what are you doing on sort of general out to 10-day weather. But for most of what people care about is what's the weather for me. And so, where I am, or where my buildings are, or where my fields are, or whoever it is that you're talking about. So I think that's really important. And for the extreme weather, what is interesting is, there's two things you can do. You can get better data and fill in the data gaps, and then you can use that, in more effective ways. Some of the targeted sensing that people are now doing for an oncoming atmospheric river, an oncoming hurricane, is to send out, balloons or drones or buoys, and to get additional data, which allows you then to, take those initial conditions and run better forecasts, and even take, historic extra observations in the important areas. And so I think that's a really interesting area, and AI's ability to take on much more data than the physics models can take, and to do so very quickly is super exciting. And so this sort of the existing physics pipeline, first of all, it's very expensive and costly, so you can only do so much computation. But also it requires this data assimilation step to take all these observations and turn them into sort of an idealized, three-dimensional grid with a data cube at each center of each voxel, on that grid. But inevitably, to do that, you're interpolating, because there are parts of the Earth we don't sense very well. Mm-hmm. So our approach at Brightband is to go back to the raw data, and instead of going from that intermediary, idealized analysis step, to go back to all the raw data and forecast from that. That allows you to take on way more data. And so that's where you can start using, even things that aren't thought of as having weather signal in them, maybe tweets. People tweet when they feel an earthquake, maybe the pressure readings from your smartphone. There's many different sources of information about the weather that are not currently captured in the traditional weather sensors.
Well, so you include things like earthquakes in your weather forecasting problem? Well,
we're largely atmospheric, but, we would like to move to the land and the ice and the oceans, and, maybe even solar or space weather. They all feed into it. And I think, that Earth system model we talk about in our mission, combines all of those things to be able to make decisions, perhaps even in the future, the biodiversity and human activities and sort of all the other things that you may be able to model and include in a picture of the Earth.
So, like, thinking about weather all day, are you someone where how does climate change factor into your models, and how does climate change factor into your personal outlook?
Yeah, I mean, climate change has unfortunately got terribly political, at least in the US. So, we're pretty practical about it. There's clearly increasingly extreme weather. And so how do we deal with that? I think as a race, we should have the tools to be able to make decisions about not poaching the planet we're on. Currently, the tools that we have are not great. It's a hard problem. And obviously the timescales are forbidden.
The timescales are pretty different, right? I mean, like if you could forecast out even 30 days, you probably wouldn't see climate change in that, right? Do you imagine doing 5-year weather forecasts or more?
The hope is that traditionally weather and climate have been modeled differently, right? And so, weather has been sort of initial conditions and then sort of auto-recursively rolled forward, forecast, and then climate has been a long-term averages, and then what's called sort of an Earth balance model, where the main forcing function is the sun's pumping in a lot of energy, and some of that bounces off the clouds and bounces off the ground, and you can make some assumptions about that, and you can make assumptions about how carbon dioxide in the air and changing brightness of the ice and other things are going to change that balance.
Although that would require some physics, right? Like, I mean, you're not going to have historical data that would show you that, or do you think the models could somehow learn that from the last 100 years of data?
I remain curious as to where we'll end up on that. I think some of the bets being made are to have some hybrid models which sort of create a physics spine, hopefully differentiable, so you can actually compute with that, and for that to stop the AI sort of drifting away from some sort of physical reality. But I think we will see.
Interesting. I mean, I guess climate change is a loaded topic in America, probably everywhere in the world. And I think one of the kind of interesting things happening right now is AI becoming an increasingly bigger component of our electrical grid energy consumption. Do you have a point of view there?
Yeah, I mean, clearly, clearly we should be mindful about how we use the world's resources, and spinning up massive amounts of compute to answer unimportant questions. We might want to think about that. I think weather's an important question. I think so in terms of priorities of what we use the world's resources for, I would sort of put it up there. The good news is the research shows that AI is 6 orders of magnitude faster and cheaper than the current approach we're using with physics. So at least on the inference side, we should be able to save a lot of energy. You can now, so the crazy thing, if there's one thing you take away from this, you can now, using a laptop in under a second, do a comparable forecast to what it takes $1 billion supercomputer hours to do.
And wait, why is that? Because of you're saying with a deep learning approach, you can do that?
The amazing ability of AI to sort of compress information into the size and amount of compute you need to apply patterns, learned patterns, to get good answers is sort of mind-blowing.
Wow. Could I download a program that would do that for me?
Yeah, I mean, you might want a beefy laptop, but
I got a pretty good one. It can run can run like a 70 billion parameter LLM. So I feel like, yeah. What would where would you point me to find?
So I mean, part of the reason we're around is a lot of these research models are not yet available for anyone to run, right?
I see.
Lack of commercial licenses or lack of tooling to make them easy to run. So there are some great models out there, and you, Lukas, I know could work out how to do it, but we want to make it easy for everyone.
So do you plan to release some of these models so that other people can build on top of them?
Yeah, early next year, we're going to open source some data model and metrics so everyone can try this.
But actually I guess the like a model you can run?
Yep.
I see. Interesting. Do you expect people to fine tune it? Maybe you could, do you imagine like a fine tuning use case? Like if I wanted to forecast weather on the moon, maybe I could take some lunar data.
I had not thought of that one, but that's pretty cool. Yeah, I mean, ideally, you wouldn't want to retrain, all the parameters. One can imagine that you have a model that understands enough about weather that if you could put in your initial conditions for your particular place of interest, that would be a fine tuning, and that you could get out a customized forecast for you. So, for the first time, you can run a forecast yourself, and it can be customized to where you care about. That's pretty cool.
Cool. I've always wished that these weather apps would have a little more of like a probability distribution or be more clear about what they're actually forecasting. I hope somebody takes your model and makes the forecast that's a little more clear about the uncertainty and what that really means.
Yeah, me too. I mean, you sort of look at these weather apps and it tells you what the weather is sort of 10 miles that way, and you're like, well, what about me?
Totally.
And, one of the interesting questions is, once you're able to run, a ton of scenarios and you have all these probability distributions for what the weather could be, like, how do you communicate that to people? And we have an advisor, Amy McGovern, who's a professor at Oklahoma, and she has spent a lot of time trying to work out how to get people to understand and trust weather forecasts. What does it mean to say there's a 30% chance of rain? Is it going to rain in 30% of the area? Is it going to be, like what? And so we also need to innovate on how we sort of communicate weather to people.
If the butterfly effect is real and you can forecast the weather well, do you think there are applications of a model like this where you could change the weather with some kind of intervention?
So, obviously you need, ways to change the weather, and there've been some of those, cloud seeding since, I think the 50s, 60s. And I think people have been sort of appropriately concerned about large scale application of those and sort of whether we know what we're doing if we go try and change the weather. But I do think when we're changing the weather right now, right?
Sure.
You and I are burning fuel to support this podcast, and that's going up into the air, and that's changing the weather. So I do think that what we need, or what maybe we can do to help in mitigation areas, is for all the different tools that we could use, how do you predict how they're going to change the weather? And there's a great book by Neil Stephenson called Termination Shock, if you haven't read it, which sort of muses on this question and sort of raises the interesting idea that whatever you do to the weather will probably not affect all people the same. And there may be winners and there may be losers, and what do we do about that, right? Because we all live on the same planet. So.
Yeah. Okay, final question. I guess this is more of an entrepreneur oriented question, but my companies have been more software based, where $10 million is like a lot of money. You could do a lot with this. I feel like your company is a little more deep tech. Maybe I'm curious how you think about like milestones and where you think the money is going to take you. Like, are you trying to get to like a commercialization stage, or are you trying to show that your technology can work for certain use cases? How do you think about that, especially in this world of large compute costs?
Yeah, so the reason we have to raise, that amount of money is both we're looking for sort of very particular talent, which is pretty sought after. The number of people who can build and run the latest AI, global weather models is sort of vanishingly small, and then the amount.
Although
of
those people would probably be excited to work with you. You seem like a great.
Well, that's
option,
cool. We've
right?
been able to, yeah, and fortunately, my co-founders Ryan Kiesler and Daniel Rothenberg are sort of very well regarded, and so it's been fun. People are really like, "Ooh, I get to work with Ryan and Daniel," so that's exciting. So yes, but then so the people, and then the amount of compute and data is non-trivial, and so what we're trying to prove with the first money that we've raised is to get to the point where we can demonstrate that we've built something that works, and that people want, and that they're willing to pay for, and therefore that it's worth investing more of our time and more of our investors' money to scale that up. So that's our goal for the next 2 years.
Awesome. Well, appreciate your time. That was fun.
Fun talking to you, Lukas.
Thanks so much for listening to this episode of Gradient Dissent. Please stay tuned for future episodes.